excited to hear what Rich has to say. Take it away, Graham.
All right. It is my great pleasure to introduce soon-to-be Dr. Rich Pauloo, giving his PhD exit seminar. Rich came here and he really thoroughly vetted the faculty, which makes it all the more surprising that he wound up working with me. But I remember him very carefully interviewing many faculty members, and he really dug into in depth, you know, what life would be like here, and you know, whom he wanted to work with. And he worked with a number of faculty, which fits with his background in part because his BS was in biology from Berkeley, and he did a minor in conflict resolution. How many of us can say that we have a minor in conflict resolution with anything else? So I think it fits Rich perfectly because he is such an affable, delightful, stimulating person to work with. And part of it is, well, there's never any conflict, but there's always lots of enthusiasm and excitement and genuine dynamic thinking. So, and I would have to say, I've watched his dynamic thinking and research mind really grow. So he's been open to growth while here at UC Davis, and it's definitely gone in that direction for him. He is one of our more decorated graduate students. And I'll go through a list of some of his awards. He's recently received a Microsoft award for his work on earth science and domestic well failure. He received an AGU Outstanding Student Presentation Award in 2020. He won the California 2019 Water Data Challenge and also won it in 2018. He won a NASA data visualization competition, NSF GRFP honorable mention. That one should have gone, but didn't quite. And he was an NSF IGERT fellow. So he's done good. He's fun to listen to. The work is wonderful. So I think we're going to enjoy this. So I'll stop it there so that Rich can get on with his presentation and his life.
Thanks for that introduction, Graham. And at least half of that is all true. So without further ado, I'll get into my presentation. First of all, just thanks for being here today at my exit seminar. And for those that don't know me, my name is Rich Pauloo. And today I'm going to talk about emerging consequences of regional scale aquifer depletion, specifically basin salinization, contaminant transport, and well failure. And thanks to all that have supported my research, travel, and scientific meetings. These are a few of their logos here. This is the agenda for the talk. I'll cover an intro and motivation for the body of work, and then I'll get into the body of work, which is composed in 3 chapters, and then I'll conclude. My research focuses on California, but the issues that I explore are part of larger global trends. So first of all, this black line, it shows global human population growth over the last 4,000 years. And in 1798, the economist Thomas Malthus speculated that world food demand would outstrip population given its exponential growth rate compared to linear growth rates of food production. And he speculated that we'd all be in big trouble. Malthus was famously incorrect because he didn't anticipate these 20th century scientific advancements in synthetic fertilizers, disease-resistant plants, and also groundwater development to augment surface water supplies for irrigation. Together, these were termed the Green Revolution, and they allowed for food production to outpace population growth, thereby avoiding the Malthusian curse. And groundwater has become essential to life during the Green Revolution and in this last century. Groundwater provides drinking water for about half of the global population and about half of all irrigation water. 2.5 billion people, or roughly 1 in 3 people on Earth, depend on groundwater for their basic daily needs. And groundwater, when I speak of groundwater, I mean water in the pore or fracture spaces of subsurface sediments. It's naturally replenished by rainfall, stream flow, irrigation recharge, and other means, but usually on very long timescales. And chronic overdraft, or extracting groundwater at a faster rate than it's replenished naturally, has led declining groundwater storage worldwide. And this can negatively impact groundwater systems in a number of ways, some of which I'll cover. Groundwater resources are ubiquitous. They're really everywhere. And so this is a study by Fan et al. And I show this figure because I want to emphasize that the issues I cover are not only California problems. So in this figure, blue indicates shallow groundwater and red indicates greater depth to groundwater, and just shows the global distribution of groundwater resources. And many aquifers worldwide are in critical decline due to drought and overdraft. This is data from the GRACE satellite, which measures mass fluctuations across the Earth's surface. And groundwater withdrawals happen to represent huge changes in mass that we can detect from space. Red colors in this map indicate declining water storage and correspond to areas of high groundwater extraction, such as California's Central Valley Aquifer right here, and other major aquifer systems worldwide. And in the backdrop of all this groundwater depletion is the specter of climate warming, which, by way of decreasing surface water availability, might increase our groundwater dependence in some regions. And California happens to be one of those regions. So these satellite images show winter snowpack, which is essentially our surface water supply between February of 2018 and 2019. 2018 was a dry year and 2019 was an exceptionally wet year. And consequently, more groundwater was used in 2018 than in 2019. California is a great natural lab, therefore, for water research because we have abundant data and models to experiment with hydrogeologic processes that also occur globally. And so then those models are transferable. And it's also a valuable agricultural hub, creating tens of billions in revenue, not to mention all of the jobs that go along with that. And lastly, according to the Public Policy Institute of California, about 85% of Californians rely on groundwater for a portion of their drinking water supply. So groundwater is important. And that groundwater is imperiled. Climate projections in California forecast an end-of-century reduction in snowpack of about 80% and about a doubling of drought frequency in the southern Central Valley. And we think that sustainable groundwater management might help, specifically this Sustainable Groundwater Management Act, or SGMA, just passed the year before I started grad school. And, but there are still many scientific questions that remain unanswered that are critical to sustainable management. And for context on the intensification of groundwater use in California, I built this animation from well completion report data. Each agricultural well is a red dot in the map that appears in the year that it was drilled. And the inset plot up here shows the number of wells drilled over time. And note that the rate of well drilling increases during droughts, such as the 76 to 77 drought, this 87 to 92 drought, and this most recent drought from 2012 to 2016. And that in 1940, around the mid 20th century, we have hardly any wells drilled at all. So this is really a new thing that's happening in California. So in summary, groundwater depletion is a serious problem with extreme consequences, which I will not cover all of these consequences, but I want to point out that some aspects, like well failure and salinization due to basin closure, have received much less attention, not because they're unimportant, but rather because the data or the models to study them either weren't available or just haven't been developed yet. And that concludes my introduction. This is an overview of my dissertation, which has 3 chapters. And now we'll get into chapter 1. So this was recently published in Environmental Research Letters, and you can find that paper at this link right here. And the title of this paper is Domestic Well Vulnerability to Drought Duration and Unsustainable Management in California Central Valley. So fundamentally, what we wanted to do with this study was assess the risk of domestic wells. We wanted to assess the risk of domestic wells running dry. So that's when a well fails. So I'll use well failure and wells running dry interchangeably. And we wanted to do that in California Central Valley. So we specifically wanted to understand how well failure would be impacted by extended droughts, so longer than what we've seen in the historical record, wet winter recharge events, which may buffer against well failure, and 3 different groundwater management regimes, so the difference between a policy of strict sustainability versus a business as usual groundwater extraction. During the 2012 to 2016 drought, pictures like this were not uncommon. Disadvantaged communities in the Central Valley were dependent on private domestic wells and suffered from well failure due to overpumping. Bottled water delivery was common, and the state paid out about $35 million in drought-related assistance, mostly for water tanks like the ones pictured here, and bottled water deliveries. And it's also very likely that the 2,000 domestic failures reported in the Central Valley during this time is an underestimate because this reporting was voluntary. So how does a well fail? This is a simplification for illustrative purposes. In reality, we have cones of depression around these wells, and there's confined systems, and unconfined systems. But for simplicity, here are two wells in figure A, and they're screened at different depths in an unconfined aquifer, and they're both active. In figure B, aquifer depletion causes the water table to drop, and this falls below the level of the shallow pump, causing this well to go dry or fail. And the deep well remains unaffected, but it's now a bit more vulnerable to failure than it was before. So the scale of the 2012 to 2016 drought, or the most recent drought, was really large in California. In figure A, this is our Central Valley study site. Blue points are the locations of all domestic wells, and red points are the locations of the 2,027 wells that were reported dry. And figure B is the groundwater level change over that time. So think overdraft, where red indicates groundwater level decline and blue indicates areas of recharge. And as we could see, most of the map is red, indicating groundwater level decline. We had incredible data for this study, including about 1 million well completion records that were recently released to the public, and over 20 years of groundwater level data, constituting more than 100,000 observations. Prior to this work, little had been done on domestic well failure modeling because researchers lacked data access. The first California-specific domestic well maps, just knowing where the domestic wells were at all, came out in 2015 and 2017, shown on this plot in the left, where red indicates more domestic wells. And shortly afterward, this data set was released to the public and improved upon. Other researchers have done amazing work with this data, making static estimates of wells that have failed in the past across the country at nationwide scales, and also at countywide scales. And a former study by Gailey et al. Right here incorporated forward modeling to test the impact of future synthetic drought scenarios. So he created new drought scenarios and tested what wells would fail. But no study had addressed the regional aquifer scale. So for instance, the entire Central Valley, testing not only the impact of future drought, but also wet winter recharge events and groundwater management regimes on well failure. So onto the methods. The first step was data assimilation. Well completion reports and groundwater level data were gathered and cleaned in the study site. And here I'm showing the location of the domestic well data and the interpolated groundwater level data just during the seasons from 2012 to 2016. So it's flipping through the seasons right here. And as you can see, we removed this section from the study area in the East San Joaquin Valley simply because there just weren't domestic wells in that area. We used ordinary kriging on the unconfined to semi-confined groundwater level and, data. And because these data follow a log normal distribution, we log transform the field values prior to interpolation and back transform them with this correction from Laurent and Journal here. And moving on, we distinguish between three classes of well conditions. There could be active, vulnerable, and failing wells. For the purposes of time, I'll only show active and failing in this presentation, but this is documented in the paper. And so basically, these different classes deal with where the water level is in relation to the estimated pump location. Because climate projections forecast an increasing probability of drought in California, and in California's past, we've seen decadal-long droughts, we really wanted to test what would happen if this 4-year most recent drought from 2012 to 2016 continued into another, 5, 6, 7, 8-year-long drought. How many wells would fail? Where would they fail? Why would they fail? So for the extended drought duration scenarios, we assumed that another 4-year-long drought would see the same spatial distribution of groundwater level decline as that observed between 2012 to 2016. So equivalent to this groundwater level change in panel B of this plot, and then we just scaled every other drought accordingly. And this is really similar to what Gailey did in his study. Next, we wanted to see if sustainable groundwater management matters. So this figure illustrates the 3 projected groundwater management regimes that we tested. And this blue line is actual groundwater level change for a point in the Tulare County as an example. And we're looking at time on the x-axis and depth to groundwater on the y-axis. So a business as usual regime projects this historical trend represented by a linear model into 2040. And a strict sustainability regime halts that groundwater level decline at 2020. And then a third regime, a glide path regime, is a moderate mean of the two former regimes. So in this figure, we're only showing the projected groundwater management regime using a linear approximation from this period, 1998 to 2017. But in the analysis, we account for three linear approximations representing our hydrologic uncertainty, because if you choose different time frames of this historical groundwater level, you can get different slopes. Now, there's also this tricky problem embedded in in this analysis, which is that the wells in the database only have a construction year. So you don't know if a well is still online or not. The well may have been retired due to age, and you can't assume they're all active because you'll overestimate the number of failures. And there's not good enough data to constrain the distribution of retirement ages. So zooming into the Central Valley, for example, the difference between a 25-year retirement and a 35-year retirement is about 10,000 wells. So rather than guess a retirement age, we calibrated the retirement age parameter, and now I'm starting to show some results here. And we were able to do this because we had real-life observations of failure data from 2012 to 2016. And that's represented in panel A. These are observed data that we obtained from the state of California. And we could run the well failure model many times and compare the spatial distribution of predicted versus observed failures during this 4-year drought. And this plot here in figure B shows our best model, which had a retirement age of 28 years and agrees with the 31-year retirement age found by Gailey in 2019 when he studied Tulare County, which is this section right here. Each plot pair is the point pattern of the failures and the kernel density estimate. So this is sort of a heat map of those failures. And we normalize the proportions between 0 and 1 just so you can see where wells fail. And then we can analyze the residuals by differencing these kernel density estimates. And so this is actually how we perform the calibration. This map here shows the residuals where blue areas are under-predicted failure, and red areas are where we over-predict the failure, and white is where the model is within a 20% accuracy, and this is the distribution of the residual error. So the residual error is normally distributed, and this suggests that it's unbiased. It's not systematically over or under-predicting failure. That's a good thing. And we also see that the majority of the error is within 20% of the actual failure proportion. And again, this is the sum of this error is what we are minimizing when we calibrate the retirement age. So the takeaway here is that there's this scale dependency of the error, which is related to the famous ecological fallacy. In other words, model accuracy depends on the scale in question, and hence this model is best viewed as a regional scale Central Valley-wide or GSA level well failure estimate, but only if the GSA is sufficiently large. We found that extended drought durations, remember we wanted to test a 5, 6, 7, 8 year long drought. We found that these extended drought durations cause increasing amounts of well failure over longer drought. Here I'm showing the point patterns and kernel density estimates of failure proportion, and more black dots indicate that we're seeing more well failure as we have a longer and longer drought, and these are the counts of well failure. So you can see that well failure is increasing with extended drought, and this makes sense. We see more well failure because the groundwater levels are already low. So I really like this plot. In this plot, we have cumulative domestic well failures from 2012 to 2016 in this left-hand side. These are observed values. So we saw 2,027 wells fail during this 4-year period that were reported. And on the right, these are our modeled or forecasted well failures from the synthetic drought simulations, the drought durations we tested. And importantly, notice that a 4-year drought from 2012 to 2016 leads to around 2,000 failures, but an 8-year drought, although only doubling the drought duration, leads to about 4 times as many well failures, around 7,300. So, and this is because groundwater levels are already low. And we also wanted to test the impact of a wet winter recharge event. So this continuous drought duration where we have no recharge is represented by this blue line, and this green line shows the wet winter scenario, showing that when we include a wet winter recharge event, this can significantly reduce well failure. So the takeaway here is that more wells fail when groundwater levels are already low and haven't had a chance to recover, and that recharge events can help groundwater recover, and this can help buffer against well failure. And lastly, recall that we tested sustainable management regimes in this lower left plot. So the columns, there's a lot to look at here, but the columns of this grid are the pathways. So this is strict sustainability, glide path, and business as usual. And the rows are different hydrologic periods to project the groundwater level trends. So this is one period, another period, and a third period. And the left plot of each pair is the groundwater level decline according to that projection, and the blue areas indicate recharge and red is decline. And the right plot of each pair is the average point pattern associated with that groundwater level. So these are the locations of all the wells that fail given that scenario. And then this number is the mean count of failing wells. So the takeaway from this slide here is that about 4 times as many wells can fail when you compare a strict sustainability to business as usual. So comparing this number, 1,500, to this number, about 6,000. And that ratio is conserved across hydrologic periods. So this is about 2,500, this is about 10,000. So hydrologic uncertainty matters, but not as much as management. So returning to the fundamental questions of the chapter, more wells failed in the extended drought duration scenarios compared to the last drought because groundwater levels were already low. Wet winters and hence recharge, such as flood mar or managed aquifer recharge, financial incentives to fallow fields, and any measures really to reduce groundwater depletion should be weighed against the externalities posed by well failure, because this recharge can mitigate well failure. And there is a paucity of research on this topic. And lastly, policy matters. We saw that a 4-fold reduction in well failure can occur comparing a business as usual to a strict sustainability scenario. And the significance of this research is that it provides the first Central Valley-wide well failure model appropriate for regional planning and an extensible approach to model well failure given 2 inputs, just the pump intake coordinates in X, Y, and Z, and the groundwater level, which can come from data or a numerical model like C2VSIM or CVHM. Those are regional models of the Central Valley, hydrologic models. And this approach can be applied to other areas contingent on that availability. But long-term solutions to well failure are still lacking. So notably, will GSAs or groundwater sustainability agencies protect domestic wells when writing their sustainability plans, and should they? Should they create funds to pay for well failure, or should households be connected to nearby water utilities? And is that physically or economically feasible in all cases? And we still don't have good answers to that question. But we were recently awarded a Microsoft AI for Earth grant to expand this work. And the goal is to build a dashboard, which I'm showing the kind of prototype here, that allows users to drill down into a specific management agency, view their minimum thresholds and minimum objectives and the wells that we forecast to fail if those levels are reached. And then you'll also be able to specify arbitrary levels of groundwater level decline and see how failure trends change. And we think this will help agencies better plan and manage for well failure, because currently we just don't have that information. So that concludes my first chapter, and now I'll jump into chapter 2. Let's get some water. So chapter 2 is called Anthropogenic Basin Closure and Groundwater Salinization, and that's a mouthful, so I'll call it ABCSAL from now on. And there's a preprint of this paper at this URL. Fundamentally, we sought to answer these questions. Can groundwater pumping close a basin? And if so, what are the impacts to groundwater quality? And 2, what are the timescales over which the production aquifer becomes regionally degraded over its entire vertical extent? First, let's talk about naturally occurring salinity. Freshwater has less than 1,000 milligrams per liter of total dissolved solids, or TDS. These are naturally occurring, and TDS can negatively impact plants and even kill salt-intolerant crops, which has prompted states like California to adopt agricultural irrigation water quality goals, such as 450 milligrams per liter of TDS. That's California's. Groundwater salinization has also been studied in terms of seawater intrusion, naturally occurring salinization of closed water basins, and other mechanisms. But in this study, we aimed to describe a fifth type of groundwater salinization, and that is anthropogenic basin closure and groundwater salinization, or ABCSAL, which is a regional-wide salinization of a groundwater basin that's created by historically excessive pumping, which closes the basin, and then that salinization is sustained by the inability of the closed groundwater basin to discharge salts. So first of all, here's some examples of naturally closed basins. They have many names like terminal basin, enclosed basin, endorheic basin, playa, and they form all over the world in regions where ET, or evaporation, is the dominant exit for water. So due to their inability to discharge dissolved solids, these closed basins become hypersaline over time, over long time scales. And these closed basins are not life-supporting places, and if you were to use any of the water here, you would need significant desalinization, which can be costly in terms of energy. And the characteristic hydrology of these basins is that ET is the only exit for water, and that they can't discharge dissolved solids. So the question is, could something like this happen in an irrigated basin as we deplete aquifers? And we speculate that open to closed basin conversion, followed by salinization, is possible under certain hydrologic conditions. So here's how that would work. In figure A, we have an open basin, and groundwater is fresh in this basin because TDS can leave it via lateral outflow, that's these arrows going in and out, and base flow to streams, or groundwater discharge into surface water. ET is also an exit for water, but salts don't leave through ET. They can only leave via these two other mechanisms. And in figure B, we've introduced some crops represented by these green dots. Additional pumping lowers groundwater levels so that the streams now lose to groundwater, so that that direction has switched from groundwater baseflow to streams, now streams lose to groundwater. And the lateral groundwater outflow begins to drain adjacent areas because you've lowered the groundwater level in the potentiometric surface, so you're draining adjacent basins. So compared to figure A, we've lost TDS outlets and we've effectively established a salt sink. And pumping and recharge will redistribute mass from the deeper parts of the system to the shallow portion of the system, and that's evaporoconcentrated and driven into deeper groundwater. And now ET is the only exit for water, in the same way that ET is the only exit for water in these closed basins, which have no outlets for groundwater. Next, we wanted to model this process to actually get at the rates at which something like this would happen. And we chose the Tulare Basin in the Central Valley as our study site. We chose the Tulare Basin because it has a history of intensive groundwater use, and there are available water budgets, historical water budgets, and water quality data to drive such a model. So this plot on the right shows the past century of groundwater storage decline. Storage is on the y-axis, time is on the x. And this blue line is the Tulare Basin. Groundwater overdraft in this basin has depleted about 140 million acre feet. So a way to think of 140 million acre feet of water is to imagine the city of San Francisco, imagine a box with that footprint, and to imagine that under 5,000 feet of water, which is 5 times the height of the Salesforce Tower. So it's 5 Salesforce towers high over the city of San Francisco. That's the approximate volume of water that we estimate has been depleted from the Tulare Lake Basin in the last century. And that aquifer depletion has changed water budgets. So here's a map showing the Tulare Basin in the southern third of the Central Valley. And I'm comparing between figure A and B, early development and modern decadal water budgets. So each arrow is either red for a groundwater output or blue for a groundwater input. And what's important to notice is that from early to modern times is that this ET term increases. So does pumping and so does recharge. And the subsurface flow across the northern boundary also increases, corresponding to greater inflow from the north because groundwater levels in the south have declined over this time frame. Also, groundwater baseflow to streams switches direction. So whereas groundwater was discharging to streams in early development. Now groundwater gains from streams. And this is consistent with what we know about the hydrology of the area. Most of these streams are all losing streams. So this is a closed basin. Hydrologically closed. This budget is a closed budget. So we didn't seek to build a new model at this stage of the research. We wanted a first order estimate of the timescales, salt balances, and the rates associated with this present day closed hydrologic budget. So if we took this hydrologic budget right here in the modern budget that I'm showing right here, if we took that budget and ran it out into the future, how long would it take to salinate the basin? So we took a simple lumped parameter approach, averaging conditions over the entire area. And this was parsimonious because the large space and time scales of interest that we were investigating and the large scale, mostly downward flow conditions in this basin. So we take this typical alluvial aquifer and all of its heterogeneity, and we reduce it to this one-dimensional mixing cell model. And we track the time evolution of the vertical mass displacement. The approach segments this system into a series of one-dimensional, vertical, stacked, discrete control volumes or cells. And in each time step of the model, water and salt masses are passed between these cells represented by these blue arrows. And we calculate new concentrations at each cell. And this is the equation we use to calculate those new concentrations. So for at a time step k+1, the concentration of a cell is the mass balance of the existing mass, the incoming mass, the exiting mass, mass from rock and water dissolution reactions, all divided by the cell volume. And the discretization of the model is driven by this time step delta t. And since the basin scale Darcy velocity decreases with depth, the cell thickness also decreases with depth. And in that way, we can have a changing vertical velocity, but also perfect mixing in each cell. We parameterize the model with the water budget and geometry and vertical velocity profile from C2VSIM, which is a 3D numerical flow model. We get the concentration of each budget term from measured field values. So for instance, the initial TDS depth profile and rock water dissolution rates were determined from salinity and depth data in the Tulare Basin. This data showed increasing salinity with depth, consistent with what we understand about mineral dissolution along flow paths. And furthermore, we simulated ABCSAL without overdraft conditions for two reasons. For one, we wanted to show that even if you halt groundwater overdraft and groundwater levels are stable, as long as the basin remains closed, salts will still accumulate. Second, if we maintain this fully saturated model, then we avoid needing to adjust for cells drying out as the water level falls. So this old transient change in storage equation from C2VSIM goes from this to this, where we eliminate subsidence flow, add some managed aquifer recharge, and reduce pumping by the residual amount in order to balance out the change in storage to zero. And these are the results. This plot shows the TDS concentration on the x-axis and the aquifer depth below land surface on the y. The red line that's moving here is the median TDS at the specified depth. And the width of the gray interval represents the interquartile range modeled from Monte Carlo simulation. And we're stepping through time here. So as time goes on, the shallow portion of the aquifer gets saltier. And then finally, this non-point source plume reaches the deeper parts of the aquifer. And this black dashed line at 1,000 milligrams per liter is the TDS safe drinking water limit, which we reach within decades for shallow systems. And then it takes centuries to reach depths greater than 100 meters. Groundwater is pretty slow moving. This represents the average salt front across the entire Tulare Basin. And in reality, you would have local heterogeneities that would drive both faster and slower salinization than we model here. But importantly, it's important to notice that there's an inversion of the initial TDS depth profile. So in the beginning, the slope slopes down, we get saltier with depth. And with this ABCSAL that we model, we can actually invert that and get saltier aquifers near land surface that gradually get fresher as you go deeper. And remember, all this happens with stable groundwater levels and delta S is 0. So slowing that previous animation, so this animation, if we were to stop this at 50-year intervals, we would get this plot here. So each panel from left to right and top to bottom is a different time step, 0 to 300 years. Depth is still on the y-axis and TDS on the x-axis. And now we're also seeing the rock and water interaction scenario, which is this purple line, where we had an extra mass source term representing mineral dissolution. And we see that that amplifies the resulting concentrations. This blue line is what we saw in the previous animation. And here are the takeaways. So first, from t equals 0 years to 50 years, which we model as the year 2010, or roughly present day, the model predicts an average shallow TDS approaching this freshwater limit. And second, in both scenarios, the slope of the TDS depth profile inverts with time and amplifies. And third, even without rock-water interactions, so even if we didn't have this purple scenario and we're just looking at this blue no rock-water interaction scenario, we still see significant aquifer salinization in decades to centuries. And it should be noted here that this is a simple model where we assume business as usual, no intervention. So these results past 50 years should be interpreted as a worst case scenario. In reality, as people encounter saltier water, they will augment surface water supplies that tend to be more fresh water based, and they'll also develop deeper groundwater that's not as salty. So we're only less than a century into this experiment, making it hard to validate, but a recent study measured increases in TDS in both shallow and deep aquifers across the Tulare Basin over the past century, and they found that shallow aquifer TDS increased and deep aquifer TDS didn't significantly change. Their measured interquartile range increase of 110 to 850 milligrams per liter in shallow aquifers aligns nicely with our estimated 365 to 759 interquartile range of increase due to ABCSAL. And the transport timescales in our study are consistent with decadal and century-long timescales determined by previous studies that used random walk particle transport in detailed heterogeneous alluvial aquifers, which I'll show in the next part of this presentation. And this gives us confidence that the simple mixing model is capturing the dominant features of the system, which should be unsurprising because we entirely parameterize this model with 3D models and field data. So returning to the fundamental questions of the chapter, can groundwater pumping close a basin? And if so, what are the impacts to groundwater quality? We've shown that groundwater pumping can close a basin, leading to TDS accumulation in the production aquifer, and that the salinization timescales are on the order of decades for shallow systems, which we define as less than 50 meters, and up to centuries for deep aquifers greater than 100 meters depth. The significance of this work is that ABCSAL threatens irrigated basins and that overdraft is not a necessary condition for ABCSAL. Also, the Central Valley aquifer lifespan was estimated at 390 years at a business as usual extraction by Scanlon et al. In 2012. And that time frame of running out of water in the Central Valley aquifer, which is actually faster than 390 years in parts where there's more overdraft, such as the Tulare Basin. But this roughly 400-year timescale of aquifer depletion is really similar to this century-long timescale of deep aquifer salinization. And so this makes us consider that perhaps a solution to this problem looks like opening up the basin by filling it up to the point where base flow to streams and lateral outflow to adjacent basins resumes, where you restore this natural flushing mechanism to prevent the accumulation of salts. But we also note that this is probably impractical for basins like Tulare, where, like I said, the aquifer depletion is San Francisco under 5 Salesforce towers of water. That's a lot of water to put back in the basin to where it can start naturally discharging salts. However, for other areas, this may be a possible management scenario, but it would take a fundamental reimagination of how we model and manage groundwater systems. And that concludes my second chapter. This is back to the overview of my dissertation, and now I'll jump into the third and final chapter. Chapter 3 is called Mean Flow Direction Modulates Non-Fickian Transport in a Heterogeneous Alluvial Aquifer-Aquitard System, and I promise I'll define some of those words. So fundamentally, the questions we seek to answer are, how do changes in mean flow direction, which can be amplified by oscillating seasonal patterns of pumping and recharge, how do these changes in the mean flow direction impact non-Fickian transport of non-point source contaminant plumes? And what I mean by changes in mean flow direction is the mean groundwater flow direction. So groundwater is moving, and how does the direction of it change contaminant transport? Second, how does 3D geologic heterogeneity interact with these changes in the mean flow direction to influence that transport? This project is motivated by the need for upscaled transport models to address contaminant transport in aquifers like ABCSAL. But there are other non-point source contaminants from nitrates, fertilizers, pesticides. And in this model, I'll show you this model that I'm demonstrating is much too computationally expensive to run at a scale like the Central Valley. So we need upscaled models. And when I say upscaled, think simplified. Upscaled models are simplified models that still give us accurate results, but that are much less computationally expensive. Current upscaled models that we have in the present day fail to reproduce tailing observed when the mean flow direction changes, and tailing is a non-Fickian effect. And most studies investigate relatively simple unidirectional flow conditions. So even though the flow directions can significantly change in a regional aquifer, most studies investigate these simple conditions, and so we lack this understanding of what happens when you change the flow direction. So I've been saying the word Fickian, or rather I've been saying non-Fickian a lot, and I might also call it anomalous transport. In the literature, they mean the same thing. Transport is anomalous or non-Fickian when it cannot be described by fixed laws of diffusion. So these are fixed laws, his first and second law, and they basically say that the diffusion flux goes from an area of high concentration to low concentration proportional to the gradient in concentration. So for example, consider this simple 2D homogeneous isotropic aquifer in which you have an instantaneous point source injection in a uniform flow field from left to right. So this is a contaminant underground, and it is stretched along the direction of mean flow, along this uniform flow direction. And then it's also diffusing in the longitudinal direction, but also in the transverse direction. So it kind of stretches out into this oval over time. And these are snapshots in time. This is nice. This is predictable. We can use fixed laws and perfectly describe this process. The problem is that we don't have homogeneous isotropic aquifers in nature. Below is an example of a heterogeneous aquifer where we have higher K layers creating preferential flow. So we have a big tracer input right here, and mass holdback occurs near the source where we have fine grained material that slow the migration of the contaminant. And we also have these higher K layers that allow fingering and preferential flow of the contaminant. And this is a very non-Fickian transport phenomenon that we would find quite difficult to model with these equations. And people for decades have failed to model these problems with these equations. So that's the difference between Fickian and non-Fickian transport. And you can measure these features with a few tools, which I use in this study. And so key features of non-Fickian transport include tailing and early arrival, and this nonlinear scaling of the second spatial moment. So if you're measuring the concentration of an arriving solute at a control plane, so if you had a control plane right here or right here, and you were measuring the concentration coming across that control plane as a function of time, in a Fickian world, the breakthrough of that contaminant would be a Gaussian distribution represented by this red line here. So for this scenario, you could even see you'd have a little bit of mass, and then you get the bulk of the mass arrival, and then you'd have a tail, and it'd be this nice Gaussian red distribution. But in a non-Fickian world, you would get this red line here, or sorry, this blue line. And so imagine measuring mass breakthrough right here, you'd get some early arrival. So you'd have an earlier than expected arrival, then earlier than expected by Fick's law. But then this mass holdback in the fines would slowly leach out over time, and then you would get this long, heavy tail, this non-Fickian tailing of the contaminant. And this complicates site cleanup for, there are contaminated groundwater sites all over the United States and the world really, where people are dealing with the legacy of contaminant plumes that have this very non-Fickian tail. So modeling these is of a lot of interest. And another thing that we can do to measure non-Fickian transport is to look at the mean square displacement of the plume. So in a Fickian process, the spatial variance of the plume, which is essentially how stretched out it is, has a slope of 1, or phi equal to 1. And you can have spatial variance increasing greater than 1 or less than 1, which correspond to super and subdiffusion respectively. So these are the ways we measure non-Fickian transport. Now, what causes non-Fickian transport? It's spatial heterogeneity, and that imparts heterogeneity on the velocity field, and it is ubiquitous across geologic media of all types, from fractured rock to porous rock, and across multiple spatial scales. So there's 6 orders of magnitude in spatial scale here where we see non-Fickian effects. And I study transport at this regional scale. So in order to get a handle on the spatial heterogeneity at this regional scale, you really have to understand the geology. So my study site is in California, and the aquifers in California were created by evolving rivers that drain the Sierra and Coast Range watersheds. Over geologic timescales, these alluvial fans deposited correlated and interconnecting high K channel networks interspersed by low K fine grain floodplain deposits. So this is not a homogeneous isotropic aquifer at all, nor is it even this aquifer down here, but rather it's a 3D connected network with preferential pathways for fluid flow interspersed with immobile stagnation zones where the mass is held back and released slowly. And this greatly influences contaminant transport in the system. So here's the 3D facies model split by the facies, which are organized by decreasing hydraulic conductivity, or K. And I'll show the full model in the next slide. But this facies model was developed using the transition probability geostatistics approach by Weissman et al. And Weissman et al. Analyzed thousands of drillers' logs and borehole data and core data and surface features to come up with this model. And it represents 4 sequences created during Pleistocene glacial cycles. And they're each separated by these laterally extensive paleosols that form during interglacial periods where soil can form, or there's pedogenesis. Paleosols have a low hydraulic conductivity and tend to act as aquitards, but they also have windows through them that facilitate contaminant transport. And I've highlighted the main portion of a feature called an incised valley fill. This is essentially a paleo channel of sands and gravels that contains all this gravel and sand glacial outwash and is a preferential pathway for fluid flow. And then I've also highlighted a side view of these paleosols, which show that they're very laterally extensive and then thin, but act as aquitards at various locations in the system. And most of the model is made of these intermediate conductivity facies, and mud here indicates clay and silt. So if you were to look along this gradient, there's also a decreasing grain size. This figure is the model, and there's a lot going on here. So first of all, there's a cutaway. This is actually filled in real life when we model the system, but I've cut away a section of the model so that you can see what's in this model. It's called the Kings River Fan model, and it's located right here in California's Central Valley. So as you can see, quite a small area, about 15 kilometers by 12 kilometers by 100 meters. And so we've vertically exaggerated this. It's really flat like a pancake. And I've highlighted these 4 representative particle trajectories. And so what is that? So these trajectories are paths that were taken by particles in the models we ran that correspond to 4 mean flow directions that we test in this study. So remember, we want to test what happens when you go from mostly horizontal flow to mostly vertical flow. Does the degree of non-Fickian transport change? Is there more stretching of the plume? Is there more tailing? And if so, why is there more stretching and tailing? And then what does that imply for how we conceptualize these systems and how we model these systems, and ultimately how we manage contaminated groundwater systems? So we alter the mean flow direction in this study by maintaining a constant horizontal hydraulic gradient across all scenarios. And then we dial the vertical gradient up or down. And there's something called the VHGR here, which is the vertical to horizontal hydraulic gradient ratio. And that's a mouthful too, so I call it VHGR. And a VHGR of 1 means there's equal horizontal and vertical gradient represented by these vectors here. And similarly, a VHGR equal to 0.1 is mostly horizontal flow. And in the other direction, we can have 10 and 100 times the vertical head gradient, or VHGR. And notice that these vectors are not to scale. And we inject an instantaneous non-point source plume 10 meters below the water table, represented here by this pink line that I'm tracing, and that'll come up in the next few slides. So onto the equations, we model flow using the 3D steady state groundwater flow equation and mod flow. We're using constant head boundary conditions on the top and bottom and front and back faces to maintain uniform diagonal flow throughout the scenarios. And we use no flow boundary conditions on the right and left faces in the transverse direction. We solve particle transport via the random walk method with the code RW3D. And we are changing this mean flow direction, like I said, by increasing the vertical gradient, which is the ratio or the VHGR. And so IV divided by IH is just saying the vertical gradient divided by the horizontal gradient. And that's what I showed in the last slide. Now, calculating the Peclet number, or the hydrofacies level Peclet number, is actually quite informative here. The Peclet number is the ratio of advective to diffusive flux. So if this number is greater than 1, it indicates that that system is advection dominant, whereas a Peclet number less than 1 indicates that the system is diffusion dominant. And this has a big impact on the transport processes. So this table shows the Peclet number for each hydrofacies across the VHG scenarios, or VHGR scenarios. And we have increasing horizontal flow as we go from 100 to 1 VHGR. And the takeaway here is that under a more natural ambient horizontal hydraulic gradient, say this VHGR equal to 0.1, low K facies like muds and paleosols have a diffusion dominant facies, and these will hold back mass. And when we have pumping and recharge that increase the vertical flow, these facies can become advection dominant, these facies that are typically diffusion dominant. So as the system transitions from horizontal flow to vertical flow, we would expect, just by looking at the Peclet number, that there's less of a dependence on diffusion to controlling the transport, and that we should see a less non-Fickian effect. And so remember, we're going to measure that. So we measured that we measured the tailing and the spatial variance and the final particle position and residence time distribution. And the tailing, this is a big equation, but what's important to notice is that there's this parameter in here, lambda. Well, I should back up. So this equation is the tempered fractional advection dispersion equation, or the TFADE model for short. And what we do is we fit this TFADE model to the breakthrough curves. And there are these fitting parameters that allow us to do that. And this is one of many clever ways to upscale the transport, or the advection dispersion equation, to make this really complex 3D process a lot more simple. And importantly, this fitting parameter lambda, it's called the tempering parameter, and it represents how mass moves from an immobile zone to a mobile zone. And so basically a smaller lambda means that you have more tailing in the system, because it's less probable that it's going to move out of that immobile zone. So we can look at the slopes, we can look at lambda, and we can also just look at the breakthrough curves and the slopes of the breakthrough curves to look for evidence of tailing across these VHGR scenarios. And the plume spatial variance, we calculate the time evolution of the centered second spatial moment, which is how stretched the plume is with this equation here. And final particle position is just where the last particle ends up. So let's get on to some results and look at some transport simulations. So to see what these transport simulations look like, I made most of the domain transparent. And notice the non-point source injection plane 10 meters below the water table. Let me stop that and just show you that plane for a moment. That's where all the particles start, 10 meters below the water table. And as VHGR decreases, the plume gets more spread out in the longitudinal direction. And we also, the horizontal direction. And we also can see some spots on this front face where we get more transport as the flow is more horizontal. And I'll show later how these spots on the front face correspond to preferential flow. So backing things up, let's see if you can see some of that's kind of hard to see here, but there are areas that the plume concentrates on the front face, and I'll show that in a bit. So onto the tailing, we measured this with a control plane on the bottom of the model represented by this pink plane. And the non-point injection, non-point source injection, was 10 meters below the water table. That's this pink line near the top of the domain. So we inject particles, a plane of particles. And we inject 10,000 particles and track their movement over time. And these are the breakthrough curves we get for each of the VHDR scenarios, or the hydraulic gradient scenarios. So figures A through D show those breakthrough curves, and the colored dots are the solution we get from solving the transport equation with RW3D, and the black line is the fitted T-fade model, and the T-fade truncation parameter lambda is in this table, and as expected, as VHDR decreases and we have more horizontal flow, lambda also decreases, indicating more tailing and more non-Fickian transport. And you can see that quite clearly on just the breakthrough curves. So these are these breakthrough curves right here on a log-log scale, and we normalize the time by this characteristic time so that we can compare across scenarios. And what we see is that as the VHGR decreases and you have more horizontal flow, there is more and more tailing corresponding to a more positive slope. So this is indicating mass that's being held back as the flow is more horizontal. And you can actually start to see that in these scenarios here. So here, let's go ahead and play that again. And another way to measure this, remember, is how stretched out the plume is. So this plot here is showing the temporal evolution of the spatial variance of the plume, which each of these colors is a different VHDR scenario. And remember, the slope of this is equal to 1 if the scaling is Fickian. So in the longitudinal direction, we see Fickian scaling for mostly vertical flow with a slope of 0.95. But as flow is more horizontal, early time scaling is super diffusive for these lower VHGR, more horizontal flow scenarios. And that starts to transition to a persistently pre-asymptotic super diffusive scaling. So the slope is still greater than 1, and it's persistent, meaning that as the plume gets stretched out in the longitudinal direction, it encounters more and more spatial heterogeneity, which holds some of the mass back and accelerates some of the other mass. And so in natural formations, some researchers have speculated that these lines never really converge onto a Fickian scaling. And so therefore, the advection dispersion equation is really inadequate to model these, and you need some upscaled method that accounts for the tailing. And what these simulations are showing is that, in fact, for sufficiently vertical flow, we might be able to get away with a Fickian model in terms of describing that transport. But for these more horizontal scenarios, we see persistent pre-asymptotic scaling, and Fickian scaling is never reached. So this is a big slide. This is probably my messiest slide here. And I'll walk you through this. So we see preferential flow in these high K gravels and sands. So figure A is the domain, and I'm making it transparent so you can see this lateral high K and size valley fill. And I've marked a few sections on the front down gradient side of the model to indicate the end of the incised valley fill and these prominent interconnecting sand and gravel bodies. So these white outlines are also these black outlines. And you can see that the hydrofacies there are gravels and sands, or high K gravels and sands. And in all of these other subplots are basically this subplot here. And these outlines correspond to these outlines. So this top row are all the VHGR scenarios from high to low. So we have more horizontal flow as you go from left to right. And the points are the final positions of the particles, colored by the exit time that they exit the domain. So it's the Z X position in this model where they exit the domain. And lighter means earlier time and darker means later time. And on this bottom row, it's the same thing, except the lighter colors mean towards the up gradient side of the model, and the purple darker color means towards the down gradient side of the model. And as what we see, the takeaway here, what we see is that as flow is more horizontal, we get more particle clusters in these highlighted black regions, which indicate preferential flow along the high K networks that terminate on this front face. And this makes sense because when we take a look at the 3D particle transport, and so now I'm showing the low K paleosols visualized, we can see that these paleosols at VHGR1 are advection dominant. And so they're actually allowing mass to move right through them. Whereas with more horizontal flow, they act as barriers to flow, and mass still gets through them. Here, I'll just let this play. Mass still gets through them, but it has to find its way through the windows. So you can see there's less mass transfer through the paleosols. Whereas for VHGR equal to 100 vertical flow, they just go right through and exit the bottom of the model. So just wrapping up here, on the right are the same VHGR scenarios, but I'm only showing 20 particles, and each color is just a different particle. And I'm highlighting the entire trajectories. So the take-home message here from this study is that we observe more non-Fickian transport under more horizontal flow in natural geologic formations, and also strong vertical gradients by way of transitioning these low K facies from diffusion to advection dominance can reduce the tailing and preferential flow. So geology matters. And this research gets us one step closer to developing those simplified upscaled transport models that accurately describe how contaminants move through groundwater. And this will help us better manage groundwater quality in basins worldwide. Specifically, our results underscore why current upscaled models of transient transport based on the advection dispersion equation fail to reproduce non-Fickian transport. So when the flow direction changes and we have this change in boundary condition, this alters the governing physics of the geologic domain with consequences on tailing and preferential flow. The results also suggest a conceptual model of non-point source transport characterized by oscillating patterns of plume migration controlled by pumping and recharge. And they suggest that the advection dispersion equation might be more appropriate to model transport when the mean flow is mostly vertical, but that again depends on the system at hand. Our plume migration simulations also indicate that pumping can significantly increase the vertical migration and hence concentration of contaminants at depth. And a promising way towards creating these upscaled regional transport models is to first understand how diffusion and advection dominant your system is, and then as necessary, incorporate changes in the mean flow direction and Peclet number into mass transfer processes. And so taking a step back, that was the last slide of my third chapter, and I'm just going to conclude here. In the beginning of this talk, I introduced this guy, Norman Borlaug. He was holding the wheat variety that helped with the Green Revolution. And writing around the turn of the 21st century, he wrote this quote, and it basically says that the Green Revolution, the continued success of it, will depend on what he called a blue revolution. And that was a revolution to secure reliable water resources. And we're still learning about the aquifers that feed agriculture and civilizations worldwide. And we know that we haven't managed them sustainably in the past century. But looking forward, research in the field of hydrogeology, or hydraulics plus geology, can produce the solutions required of the blue revolution. Hydraulics gives us these well-defined and simple physics for problems with idealized boundary conditions, but geology is complex and will remain so. It's hard to gather subsurface data, and especially at the regional scales that we use groundwater. And as we act to manage groundwater more sustainably, we will need this regional scale data, and we'll also need regional scale models that resolve enough of the geologic controls on hydraulics in order to inform critical water resources decisions. So thank you so much for attending my seminar. This really means a lot to me, and I'd now like to acknowledge a few groups of people. First, I'd like to thank my mentors, advisors, and academic coordinators, qualifying exam and dissertation committee members, lab mates, and postdocs for teaching me so much and guiding me through this maze. And in particular, I want to thank this guy right here, Dr. Graham Fogg, my major professor. For the past 5 years, I've been really fortunate to receive Graham's mentorship, his patience, his humor, and Graham really gave me space and time and freedom to make mistakes, to think independently, and to develop a sense of intellectual and scientific curiosity. And I really appreciate that. I couldn't have made it without the support of the brilliant and thoughtful and hardworking students in the Hydrologic Sciences graduate group that I took classes with and learned from and grew with. And I'm so grateful for them and also for the housemates and friends that have made Davis feel like home and that have kept me sane these past 5 years. And my family has believed in me every step of the way and encouraged me to pursue graduate education in moments of doubt. I'm very thankful for them. And I couldn't have done this without my partner, the recent Dr. Marissa Donnelly. This is her wearing a homemade cardboard graduation cap. So graduating during COVID really demands innovation. Throughout grad school, Marissa's been my best friend, my rock, and my family. And finally, I'd like to do something unconventional and acknowledge this. It's what I'm calling the dark cave of failed ideas. You can still count on Rich Pauloo to make things weird. These are a handful of the figures representing a few projects that I started, which went absolutely nowhere at all. And these failures were important stepping stones on the path to more successful ideas. And if grad school has taught me anything, it's how to persevere. I couldn't have made it through this dark cave of failed ideas and into the light without the support of so many people, including everyone on this phone call right now. And I just want to thank you so much. And with that, I'll end my presentation. Thank you for your time and attention. And now I'll stop talking and hopefully there's a question out there.
I just want to invite everyone to unmute themselves right now and give Rich a round of applause.
Congratulations!
Good job.
Good job, Rich.
Congratulations!
The blue revolution.
Oh, cool. I'm seeing your faces now. I've just been like talking at a picture of Graham Fogg this whole time.
Oh, do you want me to go back to that?
Oh, wow. Thank you. There's so many people here. Wow. Thank you so much for being here, everyone.
With the videos on, we can do the applause again.
Thank you all
Great
so
job.
Congrats!
So I've got a question.
much. Uh-oh.
Does this mean you're like the leader of the blue revolution right now? Are we witnessing history?
Yeah, that's right. PhD in the Blue Revolution.
Maybe. Things are happening. Where's the questions? You have to look at
I'm not sure who's moderating the questions. I think the seminar series will do it.
People can ask any question.
Anybody can ask any question, Rich.
Oh, anyone?
I'll ask questions if no one else will. I always got questions.
Yeah.
Okay, for real. That was a fabulous talk, Rich. I always try to ask some gotcha questions. I'm not going to do that because that was so incredible. For chapter 1, I was curious if there was any way to get like population information on who those domestic wells are serving, because clearly a domestic well failing isn't created equal if a well is serving one family. I don't want to start getting into a debate about that, but if it's serving a whole community, that is a critical well.
Right. So the wells that we modeled in the study were just private, shallow domestic wells, which are distinguished from community water systems or public water systems, which tend to be deeper and serve more people. I focus because they're really the canary in the coal mine, and they tend to fail first when groundwater levels fall. But I think you bring up a great point, which is that we don't know, and there hasn't been research as to who is affected. We know from news, media, and from anecdotal evidence that the people that are affected include members of disadvantaged communities, but no one's joined all these well failure data to census median API and tested, hey, are the people in this census tract, are census tracts with well failure more likely to have a lower median income than census tracts without well failure? And that would be like a simple t-test that someone can do. But there are a lot of interesting questions on this frontier. And one of them is also like, what do you do when a well fails? Like you can dig a well that's deeper, you can lower the pump if there's sufficient room, or you can hook up that community to an existing water supply, like a public water system that's nearby. So we haven't done the geospatial analyses to look at how far public water systems are. But I expect that in the next couple of years, someone will have to do that.
Yeah, that'd be interesting. And coupling that too with, are there other what are the other sources that would be available to those populations? Like, are we in a place where the well failing is the only source of water available, or are we in a place where maybe there's other options? Lots of cool work. Thank you.
Yeah.
Hey, Rich, this is Rob. On chapter 2, I'm wondering if you could, how much extra work it would be for your next paper to think about how redox, changes in redox would propagate with depth. And if you're familiar with some of the work by, I think it's Brett Juergens over at the USGS, as redox conditions change, uranium becomes mobilized, becomes soluble. And you're starting to have uranium water quality as water propagates to depth.
Yeah, this is a great question. I think beyond the scope of like a reactive transport model, this is a difficult question to address with the methods that we have, but certainly really important. But I wouldn't know how to begin that, actually. This is actually news to me, so I'll have to read that paper that you mentioned.
Rich, I have a question regarding chapter 1. That's actually great news in the big picture thing. If I think you said there are about 7,000 or 8,000 wells that will fail, as opposed to 2,000. Seems like that's an easy fix. Throw $100,000 to replace each well at it, which would be less than $1 billion to solve the entire problem. In the bigger picture of things, that's not so much, considering that's about the cost of what it's going to take to fix the east side canal, the Fine Kern Canal, or maybe twice the cost of just fixing that one piece. What's your take on that? I mean, if this gives the GSAs the freedom to have a reasonable glide path and farmers a little bit more livelihood, is this perhaps a way to go, is to just pay off the folks that lose access to groundwater and construct them a new well?
This is a good question. So the question is essentially, do you just pay for well failure? Do you just internalize that externality? So currently it's an externality. I think before Rob's paper in the Tulare County and before this paper in the Central Valley, and now like what Darcy's doing with these minimum thresholds, we're getting a handle on how many wells we expect to fail. And that's critical for planning as a GSA. Hey, do we need representation from the communities that are impacted, number one? And two, if we continue to deplete groundwater, there has to be some sort of contingency plan that will require research on how to how to best pay for that. But I don't know, I wouldn't take too kindly if my well was going to go dry, and I would want some assurance that that cost would be internalized somehow, and that importantly, I would just have water. I would imagine that most people would just want water and would want some assurance that the powers that be are looking out for them in some way. And so models are the start to that, because we need to estimate how much we're going to expect, where we're going to expect it, and then how much it'll cost. So that's really the aim with the Microsoft AI for Earth tool, is to get a handle on these costs, give GSAs a range of impact, and allow them to experiment with different water management strategies that will alter the well failure ultimately and help them plan around it. But yeah, excellent question.
And if you do that, if you say you're going to internalize costs and just replace the wells, you have to have some kind of enough monitoring in place so that you don't just suddenly get 500 well failures in 2 counties that suddenly you have to mobilize drillers to install new wells. Many of these are private properties, so just the logistics of getting that many wells replaced or deepened, or getting the pumps. In some cases, you can move the pump deeper, but there's going to be other costs. And Rob alluded to one in terms of the uranium. There's also new work indicating that during times of drought, groundwater arsenic concentrations are being seen to increase. Why is that? Well, it's a combination of well dynamics and the geochemistry. But there's other issues here at play that might beg the question: might it be better to avoid some of that drawdown? And when those drawdowns were computed, those so-called glide paths were the losses of water supply to some of these communities, even if it's only for a couple of months or maybe a couple of years, were those losses considered?
That's right. And in the animation I showed in the beginning of the talk that had the location of agricultural wells over time, and you saw that the rate of well drilling spiked during droughts. This essentially means, when the water levels are moving the fastest and they're declining the most and posing a threat to domestic wells, this is precisely the time that the demand for well drilling is the greatest. And anecdotally, we've heard that it's hard to get a well driller out to deepen your well during summer months and during drought because they're all booked. And they'll take a contract with a supplier that says, I need a 1,000-foot well here. So, yes. Any other questions? There are some questions on the chat too. I don't want to neglect folks that have a question on chat, but maybe.
You're gonna have to go way up in the chat because it's all just congratulations from the last like 20 minutes.
I might just read that later.
Rich, this is Meredith. I do have congratulations to everybody who supported you for this PhD, and also a question. Love the dark cave of failed ideas, and was wondering, this is a softball question, you've worked really hard for this moment. What was the most surprising aspect for you when you reflect on that dark cave?
Oh boy, I'm gonna take a look at the dark cave. The most surprising aspect? Do you mean the most surprising aspect of like any of these research projects, or that there is a dark cave?
Yes, and you know me.
Okay. The way I'm going to interpret that question is, I think that at so many times during the research, I thought, yes, this is it. This is what I'm doing. And this is going to materialize into something. And then so often I would learn that, no, this is, research entails a lot of like failure and dead ends and unraveling a direction that you thought was going somewhere. But I think over time, I've become better at identifying when something's infeasible or not based on these failures, and also a thicker skin in terms of just pushing through when I know that it's just going to take some gumption. So yeah, that's my reflection on the dark cave of failed ideas.
Awesome, congrats. I remember when you said in front of our entire audience that you were nervous about public speaking. So as Graham mentioned, seeing a lot of growth, and we're so proud of you.
Thanks, Meredith. And Meredith is the director of the West Big Data Innovation Hub, and she's supported travel and grants and has hosted the Water Data Challenge in coordination with folks at government and academia, and really just so many institutions. And so I really credit Meredith with that first chapter and inspiring the, digging into that research. And Rob too, for kind of pioneering that work. Thanks, Meredith.
Wonderful job, Rich. And thanks for being a beacon of conflict resolution in our lives, and a beacon of hope for a lot of things.
And a beacon of conflict during our meetings. Yeah.
Not really.
Yeah. Well, yeah, I'll just watch your faces if there's no question. It's nice.
Hey, Rich, I got a question.
Oh, nice. Jake, how's it going?
Hey, how's it going? Great presentation. Jen says I'm scream talking, so I'm sorry. I just am really excited. So curious what you think the obligation of GSAs is with regards to protecting against well failure for domestic wells versus a priority of managing the resource in a sustainable way. Like the GSPs I've seen so far have focused on the large groundwater users. They haven't had many requirements at all for the domestic users. And that makes sense from if you're just trying to increase sustainability of the basin. But yeah, do those domestic well users necessarily get lost in the shuffle there? Are they a priority? Can they be?
I think that's an excellent question, and that's what motivates the work. I mean, I think deep down, I sort of care about the little guy, and I see the domestic well user as being the little guy here. There are some pretty idealistic and important laws in California's, in just the law books, that there's the human right to water, which basically states that every Californian has the right to accessible, clean water for drinking water and basic needs. And something like your domestic well running dry seems to conflict against that. And so California's taken a stand that we want to provide that for every citizen, or I should say just every resident of California. Not everyone's a citizen. And some of the communities may actually have folks that are not citizens. So yeah, there is a sort of moral imperative there to take care of folks that are negatively impacted. And you're absolutely right that within these agencies that are locally forming all across the state, hundreds of agencies, not all agencies have representation for disadvantaged communities or even communities that may be reliant on private domestic wells. So I think the answer looks like increasing representation, looking around the table and making sure that there's some sort of accountability that people are represented, first of all. But then, as scientists, we can model these things and we can put them in front of policymakers and GSAs and say, this is what we found. Do you have a contingency plan? And how do you plan to how do you plan to remediate this? Because even looking at the letter of the law with SGMA, or the Sustainable Groundwater Management Act, SGMA says that there are these undesirable effects that we want to avoid, and a loss of your domestic well water supply seems like an undesirable effect to me. And I don't think many people would disagree about that. I think that this is getting some traction. The Water Foundation recently did a report where they did a similar well failure analysis. And so I think that there's some interest in incorporating this into GSPs. Great question.
I have a question. When you look back over your PhD, what are the things that you feel proudest of? Because I feel like often at the end we focus on the results, but I think a lot of the journey is where a lot of learning is done.
Oh my gosh, I quit my PhD. I actually I'm coming clean. I think I've told a couple people. I applied to other jobs and everything. Graham, this is news to you, so brace yourself. But I was having a really hard time, and I kind of wanted to throw in the towel. And I remember actually talking to Graham, kind of gently bringing it up. I didn't want to just tell him I was quitting. And I said, we were walking to the cafeteria to get lunch. And I go, Graham, I've been thinking maybe I'll just take a master's and, just thinking about it. And Graham sort of looked at me. I think we stopped on the path. And he looked at me and he was like, you signed up to do a PhD. And he just kind of held my feet to the fire for a moment. And it was an uncomfortable moment for me. But looking back on it, I could not be more grateful that he held me to a higher standard and that he believed in me. I didn't have really a background in geology or hydrology or civil engineering before starting. And I think I'm just proud that I've stuck through it, and that I really couldn't have done it without Graham and without you and friends and mentors, family, everyone that's here. So I really owe my success to a lot of people.
Well, I think some students need to wander, and that's how their creativity comes to the surface. mean, it's not for everybody, but I do enjoy letting students wander because I think sometimes it allows more creativity to occur. And in your case, that certainly happened. So that's part of those failures, right? Being able to have the freedom to try things and then but I would say after about year 2, you took off. Your imagination and your motivation took off there after about year 2.
Those first 2 years, man.
Yeah, I saw you in the classroom looking out the window.
Yep.
Yeah. All right. So if I had a beer, I would drink a toast, but here's to you anywhere. Oh, yes. Corey
Yeah.
has, but
Pre-COVID,
water.
we'd all be having drinks right now. So
Yeah, this is groundwater. So
that's right. Yeah, most of this coffee is groundwater too. I see Corey is unmuted. Does Corey have a question?
I was just gonna say, great work. You're an inspiration to me. You know, I'm a little earlier in my career, and it's just amazing to hear you now. You know, you here now.
Thanks, Corey. Yeah, I really hope that I get to celebrate with all of you at some point in real life later on. But yeah, just got a little emotional getting to the acknowledgements section. Just nice to think about just tremendous community behind everyone, really. You know, if you really start to reflect, like finding all the emails to send this invite to was really made me really grateful. So yeah, I hope you're all hanging in there.
all right, I've got to step off. Thank you, sir.
All right, take care, Grant.
We'll see you soon.
We'll see you soon.
Woo!
All right, Graham's gone. No rules.
No.
Careful, they're still recording.
Oh, yeah.
Yes, yes. I'm gonna edit all this though. Well, I think yeah, people are signing off, so I think this might be a good time to go. Hey, Will, how's it going?
Complimenting your mustache.
Oh, thank you. Yes.
Cool. Hey, great job again, Rich. I'm gonna sign off, but thank you so much for inviting me, and congratulations on your PhD.
Thanks. Well, yeah, I think this might be oh, it looks like Mike's about to say something. Yeah, feel no need to stick around. If folks have to leave, I totally get it. No, I'm not, you know, writing your names down on my blacklist as you sign off.
Good job, Rich. We loved it. We're proud of you. You nailed it.
Thanks. Mike, what kind of pants are you wearing right now?
I got my Dockers on.
Oh,
this is gonna be edited out, right?
Oh, yeah. Yeah, because I think I'm like got the
just like a true anchor man.
Yeah.
We're looking forward to celebrating with you.
Thank you. Appreciate that, Mike.
Proud of you.
Very proud. Good job.
Thanks. Yeah. All right. Well, I think I might sign off too. Thanks everyone for coming.
Thanks, Rich. Congrats. Good work.
Thanks, Claire. All right. Take care.